So in this next section, the section B, problems 1 through 6, we have the substitution method. And the substitution method is always the method we're going to use when x is approaching some real number. And 4 times, so in this case, the limit of this function, 4x plus 1, as x approaches 3, is 4 times 3, which is 12, plus 1 is 13. Let's think about that just for a second here. 4x plus 1 would look something like that. And then let's put 3 right in here. Let's zoom way in on this. Okay, so if you think about it, if you just replaced x with values that are getting closer to 3 from the left-hand side, like 2, 2.9, 2.99, and you could see that the y coordinates are approaching this number right up here, and that number right up there is a 13. And you could see as x approaches 3 from the right-hand side, the y coordinates are coming down here. It's like two cars coming towards one another, and they're going to end up, they're going right towards the same y coordinate of 13. But the substitution method is really nice because we don't have to consider the graphs of the functions. If we replace x with a real number and we get a real number, then we're done. We don't have to do anything else because these functions behave really well. They don't have any holes or asymptotes or anything like that. They are well behaved. Now, for problem number 2, I should probably also just kind of refer to this little section of notes over here to the left-hand side in this middle section. Zoom in a little bit. So on the left-hand side, substitution, if the limit is when we're approaching a, then we always try substitution first. If you get a real number, you're done. If you get 0 over 0, then you have to do something, and that's what we're going to see, I think, for the rest of these. We're going to get 0 over 0 for most of the rest of them. And again, just replacing x with 2 in problem number 2 here, we have 2 squared is 4, 4 minus 4 is 0, 2 minus 2 is also 0. But if we notice that we can factor the difference of squares up on top, and once we factor the numerator, we get x plus 2, x minus 2. The x minus 2's get to cancel, and then we can replace x in the reduced form of this fraction and to find our limit. There would be a hole there, so we've done that before already this year. So the limit as x approaches 2 of this function is the same as the limit as x approaches 2 of x plus 2. And then when we replace x with 2, we get 2 plus 2 is 4. So the limit is 4. And then same thing here with number 3. If you replaced x with negative 2, you'd get 4 plus 6 is 10 minus 10 is 0. Negative 2 squared is 4 minus 4 is also 0, so you get 0 over 0. Anytime you get 0 over 0, that's your cue that you need to do something. When we have a rational function, typically that means we're going to factor and cancel. So x minus 5 times x plus 2 over x minus 2 times x plus 2. So the x plus 2's cancel, and then when we replace x in the reduced version of this fraction, negative 2 minus 5 is negative 7, negative 2 minus 2 is negative 4, and negative 7 over negative 4 is 7 over 4. All right. And then replacing in problem 4, replacing x with 9, we get 9 minus 9 is 0, divided by radical 9, which is 3. 3 minus 3 is also 0. So if we remember, we talked about this, multiply by the conjugate. So we're going to multiply top and bottom of this fraction, radical x minus 3 times radical x plus 3. So radical x plus 3 is the conjugate. Now, we did a couple of these in class. When you multiply these two together, you get x minus 9. So I'll let you do the work for that. The x minus 9's cancel. So whenever you do this, whenever you're going to multiply top and bottom by the conjugate, make sure you don't multiply out these factors in the numerator, because you're going to have to end up factoring it anyway. So leave those alone, but then multiply multiply either the numerator or denominator in this case, whichever one started with the radical, that's the one you multiply together. You FOIL those, and when you FOIL those, you end up, the radicals go away, and you get this nice clean x minus 9, which cancels with one of the factors in the numerator. Then we replace, in the reduced version of this fraction, we replace x with 9 here. So we get radical 9. That's 3. 3 plus 3 is 6. So 6 is the limit. There would be a hole in the graph at that place. Just like anytime we have 0 over 0 and we factor and cancel, or we multiply by a conjugate and cancel, there would be a hole right there at that, because the limit exists, but it's not, the function is not continuous at that point. Alright, so then for problem 5 we can see we get, if we replace x with 0, we're going to get 0 in the numerator, 0 in the denominator. So we're going to, again, multiply by the conjugate. The conjugate is the radical minus 2 here, which means the conjugate is radical plus 2. So the conjugate is radical 4 plus x plus 2. It's getting a little messy in there. Again, multiplying these guys out, we just get x. I'll leave that to you. You get 4 plus x minus 4, which is just x. So those go away. X divided by x, you have a 1 in the numerator, then you have all this stuff in the denominator. The x's cancel. Now when we replace x with 0, we get 1 over 4, radical 4 plus 0 plus 2, which radical 4 plus 0 is radical 4. Radical 4 is 2. 2 plus 2 is 4. Okay. And then finally, this looks like it's going to be tricky, but 4 times pi over 4 is just pi. Tangent of pi over 4 is 1, so we just get pi. No need for any factoring or conjugates or anything like that.